All right, let's do a few problems with pressure, but before we get to pressure, I've got to deal with what's called weight. The weight of something is the mass of that object in kilograms times the acceleration due to gravity. And we give that the symbol little g, and that's a very well-known value. It's been measured since the time of Galileo 400 years ago. So the value is 9.8 meters per second squared. And so that's called the acceleration due to gravity on the Earth. You can't really read that very well. The weight is measured in newtons. All right, so let's do a quick example. So let's say we had 100 pounds. I'm sorry. Yeah, I'm doing the wrong thing. Let's say we had 100 kilograms. All right, so kilograms are units of mass. And so if we multiply that times 9.8, right? So that becomes, you just move the decimal place 2 places. So it would be 980 what are called newtons, right? So that's fine. Just to give you a comparison, here, let me show you. I think I already brought this up. So you can just type in, 1 pound to newtons in Google, and Google will give you the conversion factor. So you can always, and you can do this with various things. You can find the conversion factor. So 1 pound is 4.448 newtons. All right, so that's the way this works. All right, so we have 980 newtons, and we know that 1 pound, that's 1 lbs. That's supposed to be a B. 1 lbs is 4.448 newtons. The newtons cancel, right? Just like I did here. And so that turns out, so if somebody had a mass of, if something had a mass of 100 kilograms, its weight would be 980 newtons, or that would be 220.3 pounds. All right, so let's we like I said, we really won't use pounds very often. I just wanted to give you a quick conversion between newtons and pounds to show that it is something that you can do. All right, so we'll go back with this 100 kilograms and 980 newtons. All right, so the idea of pressure. All right, so let's do this. Don't save. All right, so this idea of pressure. So it's just P is pressure. It's the force, which in the case of something just sitting on the ground, it's weight divided by the area. All right, and so this is usually measured. The force is measured in newtons, and the area is measured in meters squared. And that actually has its own. It has a special. It's called. It's its own unit. A newton divided by a meter squared is called a Pascal, after the French mathematician and scientist Blaise Pascal. So it's capital P, lowercase a. So those are units of Pascal. All right. So let's just say that we have some kind of block. All right, and we know that. So this is a three-dimensional object. I'm not very good at drawing, but you get the idea. All right, so there's a three-dimensional object, and the area, the surface area that is touching the ground. All right, so it's laying on the ground. It turns out the area is exactly 1 meter. The area, so it's 1 square meter. All right, so if the mass if the mass of this object, so this object has some mass, and again, let's say it's 100 kilograms, just to make our lives simple. We know that the weight, which is the force, the force, also known as the weight, if it's just laying on the ground, that's the weight, is going to be 980 newtons. All right, so 980 newtons. And the pressure is going to equal 980 newtons divided by 1 meter squared, which of course would be 980 and they're called pascals. So a pascal is a Newton per meter squared. All right, so that's supposed to be a 980. All right, so now let's observe this. So pressure depends on the force, right? So the force in this case is just the weight of the object divided by the area. Now let's say that like if this was a rectangular block, and now I stand it on one end. Okay, so this is the ground right here, but now this thing is on the end. So this was the area right here, but now this part right here is what's touching the ground, and so that's some new area. Here, I'll call that A prime. I don't really care. But let's say that when you turned it on the end, on one of the ends, it doesn't really matter. It now has. I'm just going to make it smaller, okay, just to demonstrate how the pressure changes. Let's say that now it's only like a quarter of the area that it was. All right, so now it's 1/4 of a meter squared. All right, so that it depends on what the dimensions of the side of this box are, but and now so that's of course 0.25, right? Because that's what 1/4 is of a meter squared. All right, so now what happens is, so this is so we call this one A2. So I'm going to call this pressure, or I call this A1. So this is going to be pressure 1 is going to be, again, it's the same weight, so it's 980 newtons divided by 0.25 meters squared. All right. So remember, when we divided by 1, it was 980 Pascal, but this is going to be much, much more. In fact, this will be 4 times more, as we're going to see in just a second, right? Because this is 1/4. It's in the denominator, so it's really just 4 times 980. All right, so let's just see this. So it's 980 divided by 0.25. That's the same as multiplying 980 by 4, and there it is. So now the pressure, right? So all we've done is we flipped this thing on the side, and the pressure has gone up dramatically. The pressure is now 3,920. So 3,920 Pascal. All right. So that is a demonstration of what, just by changing the area, the pressure can go up dramatically. Right. A good example, another example of this, and we don't have to do a numerical example. Like, you just think about your weight, and you're standing on, your 2 feet, and then let's say you get on your tiptoes, right? If you're on your tiptoes, the pressure on your toes is much, much greater than when you're on your feet, and the entire area of your feet is touching the ground. All right, so that's a good problem. I'm going to set up another problem here. All right, so the pressure, the air pressure at sea level is 1 atmosphere. Let me write that here. So the air pressure is what we call atmosphere. So people use this in physics. They also use an atmosphere of pressure in chemistry. But what that is in pascals is 101.3 kilopascals, or 101.3 times 10 to the third pascals. So let's prove that. I'm going to prove that right now to you. All right. And so this experiment was done long, long ago by a guy named Torricelli. He was an Italian. I think he lived about 350 years ago, something like that. Anyhow, he took some mercury, which is not a good idea, by the way. He took some mercury. Mercury is liquid at room temperatures, and the specific gravity of mercury is 13.6. So all that means is mercury is 13.6 times heavier than water. All right, so that's all you need to know. All right, so well, that's one of the things you need to know. All right, so that tells us of course the density. So the density is the symbol rho for H2O for its fresh water is 1,000. All right, and then the units there are kilograms per. Remember, it's density, so it's mass divided by volume per cubic meter. All right, so the density of mercury, which is the chemical symbol Hg, you can look that up on a periodic table, is going to be 13,600, right? Because it's 13.6 times the density of liquid water, and it's of course kilograms per cubic meter. All right, so that's the important thing for this one, that you know that. And so remember, this number is what we're going to prove. All right, this is what Torricelli proved. All right, so he took a test tube full of mercury, and he filled it all the way to the top, and then took like a bath of there was another container full of mercury, let's say. So here's our container full of mercury. So this is the Hg, and he takes his test tube, which is only exposed on one side, and he flips it over, and so this is the opening right here, and he finds that, of course, this is closed right here. He finds that the mercury, so the mercury is right in here, Hg. He basically invented the first barometer, all right, and he found that the mercury inside of the barometer, inside of this test tube, would rise 76 centimeters. 76 centimeters. Keep in mind, 76, that's a C. 76 centimeters is 760 millimeters, just to let everybody know, which of course is 0.76 meters. All right, so you'll see why I'm doing that in just a second. All right, so this part right here, remember, this was completely filled with mercury. This is a vacuum inside of here, because this is closed off. This is glass up here, and this is exposed to the air, right? And so there's an air pressure that is pushing down on this bath of mercury, and that's what's causing the mercury to rise in this thing, and it'll only rise so far, and it rises up 76 centimeters. So with that knowledge, 76 centimeters, the fact that mercury has a density of 13,600 kilograms per cubic meter, we can figure out what the air pressure is. All right, so that's what we're about to do. All right, so continuing this problem, the pressure in the air is going to be the density of mercury, which we know to be 13,600, times the acceleration due to gravity on the surface of the Earth, which is 9.8, times the height that the mercury rises. And so when you multiply all that out, you get, let me just show you. So I've just put these numbers in the calculator, so you get 101,292, blah, blah, blah. So if this is typically rounded to 101.3, so you can see that's where the 0.3 comes in, 101.3 kilopascals, right? So, 1,000. So it would be 101.3 times 10 to the third pascals. So that is what one atmosphere of pressure is. One atmosphere is the equivalent of 101.3 kilopascals. All right, so there's a few problems with pressure and density.